Hey friends, now we have done with Newtonian part. We are now going to begin the Lagrangian formalism. So this form is quite similar to Newtonian formulation, but it is based on energy. It is easier to apply in difficult problems or many body situations. Now here we will mostly be using the generalized coordinates, the generalized momenta, which is given, generalized coordinate which is given as qi, or let's just call this q, the generalized momenta p, the generalized velocity q dot. And so generalized coordinates may or may not be same as the Cartesian coordinates that we are familiar with. So generalized coordinates are a suitable set of coordinates or variables which are required to describe the state of the system or the dynamics or the motion of the system. Now the Lagrangian is given by L is equal to T minus V. T is the kinetic energy and V is the potential energy, where this L is actually a function of Q, Q dot and T, that is the generalized coordinate, the generalized velocity and the time. Thus, if this Lagrangian is given, or if we can find the Lagrangian from the kinetic energy and the potential energy or potential, then the problem can be solved using the Lagrange equation. And Lagrange equation is given as d by dt of del L upon del Q dot minus del L upon del Q is equal to 0. Since there are many coordinates, let's take some jth coordinate, generalized coordinate. So this equation is called as the Lagrange equation. But one thing you have to remember is that the Lagrangian L is not a unique quantity. It is not uniquely determined. Therefore, for a given system, we can have a Lagrangian L, we can have a Lagrangian L dash also. But when you solve this Lagrange equation for both L and L dash, then the solution is going to be same, and that solution is called as the equation of motion. So that is, when you solve the Lagrange equation for both the two Lagrangians for a given system, then they will have the same equation of motion. So you don't have to get scared if your Lagrangian is not coming exactly same. The equation of motion has to come same. Also, now we can write the generalized momenta and relate generalized momenta in Lagrangian as the generalized momenta Pj dot is equal to del L upon del Qj, or you can write Pj is equal to del L upon del Qj dot. That means, for example, you can write P theta is equal to del L upon del theta dot, or you can write P theta dot is equal to del L upon del theta, or you can write in terms of x, so Px will be equal to del L upon del x dot, or Px dot is equal to del L upon del x. This Lagrange equation is actually quite easy to solve, and it uses the generalized coordinate, thus it reduces the complexity of the problem. So when you use generalized coordinates, it reduces the complexity of the problem. That is the advantage of using Lagrangian formalism over Newtonian formalism. Some points to remember: we can define a function which is s is equal to, from some t initial to t final, L dt, where this s is called as the action. The action can be defined as time integral of L of the Lagrangian from some initial time to final time. The action variable is given by j. J is equal to closed integral pi dq I. Now we have generalized force also. If you have a system and capital F is the applied force on the system, which results in a displacement of, let's say, dl, then the work dw will be equal to summation over I Fi dot dli, right, on all the I particles, on all the particles. In terms of generalized coordinates, we can write this dw as summation over j qj dqj. This is the generalized coordinate, this is the generalized force qj. Now these both are going to be equal. When you equate them, we will have dot dli bar. From this you can get qj as equal to summation over I Fi dot dli divided by dqj, where this qj is a component, one component of the generalized force. We can write this qj and relate it with kinetic energy T also, as qj will be equal to d by dt of del T upon del qj dot minus del T upon del qj, where T is the kinetic energy of the system. In terms of generalized potential, we can write this as d by dt of del u upon del qj dot minus del u upon del qj. You can use this equation when the potential is not known but force is given. We can write the kinetic energy T, which is half mv squared, in terms of different coordinate systems. In terms of Cartesian coordinates, we can write this as half m x dot squared plus y dot squared plus z dot squared. In terms of spherical polar coordinates, we can write them as half m r dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared. In terms of cylindrical coordinates, we can write this as half m r dot squared plus r squared phi dot squared plus z dot squared. We can also write the acceleration. The acceleration A, it is having two parts, the radial part in 2 dimensions, okay. In 2 dimensions, the acceleration we can write as the radial acceleration AR will be r double dot minus r theta dot squared, and the transverse acceleration A theta will be equal to, or no need of this, r theta double dot minus 2 r dot theta dot. So how I got this is, you can take the velocity in terms of the spherical polar coordinates in 2 dimensions, that comes out to be r dot r hat plus r theta dot theta hat. Now you differentiate this with respect to time, you will be differentiating every term here also, and substitute for what is dr hat upon dt, what is d theta hat upon dt, you substitute all that and you will get the acceleration A, which will be ar r hat plus a theta theta hat. So that will be ar in terms of r hat plus a theta in terms of theta hat. This will be the radial part, this will be the transverse acceleration. One more important point here is the concept of removable coordinate. So we have cyclic, removable or ignorable coordinates. What it says is that if the Lagrangian L, which was t minus v, it contains the qi dot term but it does not contain qi term, then this qi coordinate is called as the cyclic or removable or ignorable coordinate. And if that is the case, then the corresponding pi is going to be conserved. The corresponding generalized momentum or canonical momentum or conjugate momentum is going to be conserved. For example, if you had the Lagrangian as half m x dot squared plus y dot squared minus mgx. Now you can see x dot is also present and x is also present. Y dot is present but y is absent here. So this y is a cyclic coordinate. and the corresponding momentum Py is conserved. I can prove that by taking Py dot as del L upon del Y. We know this formula. There is no y term, del L upon del Y is 0. So if Py dot is 0, this implies Py is equal to constant, right? Thus the corresponding generalized momentum or canonical momentum or conjugate momentum is going to be conserved. That's it. We will stop here and we will continue with this in the next part.